Hello and welcome to our talk, Responsible Machine Learning in Production. I'd like to introduce myself. I'm Catherine Nelson. I'm a senior data scientist at Concur Labs, part of SAP Concur. I'm a co-organizer of Seattle PyLadies. I've co-authored an O'Reilly book called Building Machine Learning Pipelines, more about that later. And I'm a Google developer expert in machine learning.
Hi, my name is Hannes. I'm a colleague of Catherine at Concur Labs. I'm a senior machine learning engineer. Like Catherine, I'm a Google developer expert in machine learning, and I had the chance to co-author 2 machine learning publications in the past. One of the publications is Building Machine Learning Pipelines, which we just recently published with O'Reilly Media, and it's now available as a print or digital version. In this publication, we go through the steps you can automate your machine learning processes beyond the training of a machine learning model, and more to that later. So here in this talk, we would like to talk responsible machine learning. And we have seen all these different articles in the past where we have seen where machine learning failed to treat everybody equal and to be responsible. Whether it's a machine learning tool to hire new candidates, or whether it's a CBP using recognition systems to classify folks.
But first things first, before we get into the meat of this talk, we want you to stop and think about whether your product is ethical. If it's not a responsible thing to do in the first place, none of the techniques and methods that we're going to describe are going to help you. For example, a high-profile story recently of something that's ethically problematic is HireView, which is a tool that uses your speaking voice, your word selection, and even your facial movements to score candidates on whether they should be hired for particular roles. And if you're working on something like this, then I don't think you can claim to be responsible, even if you use all the techniques that we're going to describe. So what we're going to cover in this talk and what you'll learn from us in the next half an hour is how to set up a machine learning pipeline that takes you from your input data to a deployed model, all the steps that go into that pipeline, and how various methods in the responsible machine learning space fit into that pipeline. We're going to talk about biased data, privacy-preserving machine learning, model fairness, model explainability, how to get human reviewing your model, and how to generate an audit trail so that you can track all the decisions made by your model, and how metadata underlies all this and helps bring the pipeline together. And Hannes is going to start by describing all the things that go into a production machine learning pipeline.
To start with, let's take a look at what we mean with production machine learning. In this case, we're taking a machine learning experiment and taking this into a real-world scenario. When we deploy machine learning models, we have the chance to capture more data. We can retrain our models, and in that case, we need the scalability of machine learning pipelines to handle more incoming data over time. At the same time, we would like to produce machine learning models always in the same reproducible way. Currently, these processes are handled through manual scripts, often as Bash scripts or Python scripts. But if we express them through machine learning pipelines, we have the chance to automate the execution and to make sure that every production of a machine learning model is reproducible. And in the following slides, I would like to show you how we can do this. When we talk about machine learning in the past, we often have focused on the machine learning itself, like the architecture of machine learning networks. But when we bring machine learning to real-world scenarios, we have to consider a tool chain of other tools, libraries, frameworks, etc. For example, to handle our data ingestion, data verification, feature engineering, and the model verification leading to the serving of the machine learning models. That's what we consider these days as machine learning engineering, where we build a set of tools around our machine learning models. With machine learning pipelines, we get the chance to automate a lot of those steps and to also link them together so that, for example, the data verification is not happening before we have ingested new data. Machine learning models in real-world scenarios are often going through what we call a machine learning life cycle. Everything starts with the data ingestion. Our machine learning models heavily rely on the data we provide them for their training purposes. But in those machine learning life cycles, we ingest new data with every new model version. We make sure that the data is consistent with the statistics we've seen previously, and we also make sure that the schema of the data itself hasn't changed. Once everything is confirmed and we have made sure that the statistics and the schema are similar to the previous runs of our model versions, then we can do the feature engineering. We can convert our real-world data into something what our machine learning model can understand. After the training and potentially the tuning of the machine learning model, we need to make sure that the model performs in a way we expect it to be. And so that's happening during our model analysis step. In that case, we go beyond just calculating the accuracy or maybe the training loss to say that a model is performing well. Following the model analysis, we then compare the results of our model analysis with previous runs, because in this case, we need to make sure that not just the model is performing well, but it also needs to perform better or equally to previous runs. And that is a key difference in machine learning life cycles or machine learning pipelines to, let's say, software pipelines, where we don't have to compare a software build to previous runs. And once everything is looking great, we can then deploy our machine learning model by either pushing it to an artifact store so that it could be used in a mobile environment, or we can deploy it through a machine learning server like TensorFlow Serving. And then again, once the machine learning model is out, we can then capture more data and restart that life cycle again with new training data and create a new model version. Those life cycles seem to be pretty extensive when we want to express them through scripts or Python setups. But this is where TensorFlow Extended helps us to abstract those components or those steps as components, and then we can run those components on orchestration platforms. In this case, we can use a Python abstraction to define our pipeline steps. TensorFlow Extended comes with a right range of pre-configured or pre-existing components, but it's also highly flexible. So if you want to build your own components for your custom use cases, you can easily do that in various ways. And then on top, it supports already a number of orchestration platforms. We'll talk about this in a second. So if we take a look at the details of TensorFlow Extended, each component or each pipeline step is then represented by various components which we can use in our pipelines. But on top of that, TensorFlow Extended is also providing us standalone libraries. For example, TensorFlow Serving or TensorFlow Data Validation. The later tool can also be used outside of the TensorFlow framework. For example, in conjunction with a scikit-learn project or a PyTorch project. Then once we have defined our pipelines, we can then orchestrate our pipelines through orchestration tools. Standard tools will be Apache Beam, Apache Airflow, which is often used in various companies and projects already for ETL processes, or through Kubeflow Pipelines, which is available through the Kubernetes environment. If you want to run a pipeline in a very simple manner, you can also use it in Jupyter Notebooks through an interactive context. But in this moment, you as a human, you are the orchestrator of your pipeline. What are the alternatives to TensorFlow Extended to express those machine learning pipelines? There's the Ray project. There's MLflow from Databricks. New projects have emerged from Netflix. One of them is called Metaflow, which allows you to abstract some of those component steps. And then, of course, there's always Kubeflow Pipelines in conjunction with Argo to coordinate the execution in the Kubernetes environment. But what we have felt is that none of those projects so far get to the extensions what we see with TensorFlow Extended. We don't see as many components as we currently have available in the TensorFlow Extended environment. So how does it look like in a real-world scenario? We can quickly define our ingestion component. In this case, for example, we want to make sure that all the data we ingest, we want to split this into two data sets. We want to have a training and an evaluation data set with the given split of 3:1, and that split would be random. In this case, we define our external input path In this case, it's a file path to our file system, but it could also be linked to a cloud bucket on AWS or a Google Cloud. And then we can ingest our data through a pre-configured or given components. In this case, we use the import example generator, which allows us to ingest TensorFlow records into our pipelines. If you use, for example, CSV files, or you want to load data from BigQuery databases or other databases, there is a great number of components already existing you can use to configure your pipelines. And again, if a solution isn't existing right now, you can always implement your own implementation. And then we can use that ingested data, build some statistics around it, and then use the statistics to build a schema. And those statistics and schemas can then be visualized in tools like TensorFlow data validation, which will Catherine explain in a couple minutes here. Let's fast forward at this point in time. In the interest of the short amount of time we have, you can also express your feature engineering, model training, model analysis, and your model deployment through similar components. And once you have defined those components, you would take them, as I show you in the next slide here, and then orchestrate them again on one of your orchestrators you can choose. In this case, we take the pre-configured components, which we just configured, connect to a metadata store. In this case, we use SQLite, or you can use MySQL, configure our pipeline, and then we can then execute our pipeline. In this case, it's an example to run it on Apache Beam. Once you execute it on Apache Beam, you can then see the orchestration. Here's a quick snippet where we see all the dependencies of the components. This allows us to execute our machine learning pipelines consistently and reproducible with every individual pipeline run which outputs new model versions.
So Hannes has shown us all the steps in a TFX pipeline and how we can orchestrate them. And now I'm going to move on to talk about the responsible methods that we can include at different points in the pipeline. The first thing that we want to do is look at data on its way into the model at the data validation step. And this is where we can check whether our training data contains harmful biases. We'll also check whether the model is biased after training in the model analysis step, but we should also check our data before it goes into the time-consuming training step. There's a couple of questions we want to answer here. Firstly, is my model reinforcing some harmful human bias? For example, in the case of the Amazon hiring tool that we mentioned earlier, the model saw more information from male candidates from female candidates, and it reinforced the gender disparity in hiring for tech roles. And secondly, is my dataset representative of my target users? This is often more of a model performance question, but we do want everyone to be getting a good experience from the model that we're putting into production. And TensorFlow data validation can help us answer these questions. As Hannes showed earlier, this is a visualization tool that plugs directly into our TFX pipeline, and we can use it to visualize the statistics of our features and the distribution of our input data into the model. And we can see the distribution of our categorical and numeric features in this diagram here. But to help identify biased data on the way into the model, we need to break it down further and look at the distribution of the values within each feature. And this way we can identify imbalance between the different categories. In this example, we have a categorical feature that's the US state, and we can see that we have a lot more data from California than from anywhere else. This might be our product, but it might bias our model towards the preferences of people from California. One thing I'd like to point out here is that even if your model is using text or image data, you could still include categorical data like this as an extra feature, and this will help you track these differences between groups. In TensorFlow data validation, we can plot the statistics for one slice of the data against the values for the overall data. Here we're plotting the data for California against all the examples, all the rest of the data. And we can see if there's significant differences between the California data and the rest. We can see that in the subproduct feature, there's a higher proportion of missing data for California than for the rest of the data. And this can be a subtle way for bias to enter data when it's missing. This can mean that when the final model is trained, its performance is worse for California. And as we mentioned earlier, TensorFlow data validation uses a schema to enforce that the data entering the model fits the parameters we define. And this is a point where we can stop biased data even entering the model. If we're aware of something that can reinforce a harmful real-world bias, we can set the parameters of this data. And if our input data is outside these parameters, the pipeline will stop at this point and the model will not be trained. Next, we're going to look at the model training step in our pipeline. There's a number of different options for privacy-preserving machine learning, including differential privacy, encrypted machine learning, and federated learning. But right now, they don't integrate very well with production machine learning systems, including our TFX pipeline. The one that's most mature and closest to being integrated is differential privacy. And that's what we'll describe here within our model training step. There's a few things that you need to consider when you start thinking about privacy-preserving machine learning. You should always have consent from users to use their data, but you should also check that you're not promising complete privacy. In the method that we describe here, we'll still see the raw data that's collected from the users, but we'll prevent user data from being exposed in the model's predictions. You also need to consider laws and regulations here that might apply to you. For example, the EU's General Data Privacy Regulation or the California Consumer Privacy Act. A lot of the choices for privacy-preserving machine learning depend on who is trusted with the personal data. In some situations, users may not want sensitive data to leave their device. And in some situations, there may be a trade-off between privacy and accuracy. More private models may be less accurate, but this difference might not be large. So in this talk, we're going to consider differential privacy as our privacy-preserving step in our training. Well, what is this? Well, it's a formalization of the idea that a query shouldn't reveal whether a person is in a dataset. The probability that a query or a transformation gives a certain result is nearly the same on both of these datasets. One of these has the central person, and the other one doesn't. And the idea is that if your personal data doesn't affect the result of something, then you're happy to include it in the model because there's some deniability. Or to put it another way, this gives you the ability to say that an output of the program was just as likely with my data as without it. And this is achieved by putting some kind of randomization into mask an individual's data values. There's many different ways to achieve differential privacy, but one of the simplest ways is randomized response. And the way this works is that if there's a question that has a sensitive answer, such as, did you stay out late last night? Flip a coin. If it comes up heads, you answer truthfully. If it comes up tails, you flip again and answer according to the coin flip. And because we know the probabilities, if we ask a lot of people this question, we can then back calculate the proportion of people that stayed out late. And this gives people deniability because they could say that they just answered randomly. And that way they don't lose privacy. But this method isn't so great to add into our machine learning training step because we've only got an overall statistic. What is a good way to add privacy here is TensorFlow privacy, which lets us train differentially private models. It offers strong mathematical guarantees that prevent the user's data being memorized, but still maximizes model accuracy. And it's useful here because it fits in easily to our existing workflow. To use the differentially private version, you just need to provide different optimizer and loss. We're using a Keras model here, and this shows the new optimizer and the new loss function that we're passing in. But then we can just compile and train our model just like any normal Keras model using model.compile and model.fit. But what's going on here? Well, TensorFlow privacy introduces two new hyperparameters on top of the normal ones that you'd already use, like learning rate. And these are gradient clipping and adding random noise. We don't want the model to be affected by outliers because those can be linked back to a person. They mean that the model can be affected by whether one person is included in the model or not. So for each mini batch of the data, part of a batch, the gradients are clipped, they're averaged, random noise is added, and then they're passed to the model to update the weights. But we also want to measure how private our model is. And this uses the epsilon concept, which is central to differential privacy. And epsilon is one of the parameters that measures how including or excluding any particular point in the training data is likely to change the probability that we learn any particular set of parameters. And this gives us a bit of a privacy accuracy trade-off. As you decrease epsilon, the transformation, the model becomes more private. The accuracy can decrease at this point. And in our experience, it's often not linear. You get to a certain value of epsilon, and then the accuracy decreases dramatically. After a model is trained, the next step in the pipeline is to analyze its performance. This is a really crucial step for us, where we can check that everything is as it should be before we move on to deploying the model. And we can consider here whether our model predictions are fair. But what does fairness mean? Here's a few common definitions. Demographic parity means that decisions are made by the model at the same rate for all groups. For example, men and women would be approved for a loan at the same rate. Equal opportunity is where the error rate in the opportunity giving class is the same for all groups. For example, of the people who can pay back a loan, men and women would be approved for a loan at the same rate. And equal accuracy says that some metric such as accuracy, precision, or the area under the curve are equal for all groups. And when we say groups, this can be different types of customers, product users from different countries, or people of different gender and ethnicity. In US law, there's the concept of protected groups, where individuals are protected from discrimination based on the groups of gender, race, age, disability, and so on. But groups of people are never clean-cut in the real world. Everyone has a complex story. Someone might have changed their religion or their gender during their lifetime. Someone might belong to multiple races. And you want to look for these edge cases and give people ways to tell you if they have a poor experience with your model. A high-profile example of an unfair model in the real world was highlighted by the Gender Shades project in 2018, where they found that the accuracy of commercial gender prediction algorithms was very different across different groups, with the worst performance for darker-skinned females. The companies did improve those models after this study, but we should aim to spot these problems before we deploy our models into production. And one tool that helps us with this is TensorFlow model analysis that plugs into our TFX pipeline. And after we've trained the model and saved it, we can call TFMA to produce a visualization that will help us with in-depth model analysis. And this is the visualization that we get. You can see that our metrics, the accuracy and the number of false negatives, are sliced by the different product categories in this feature. Being able to easily slice our analyses on different categories is absolutely crucial for checking whether our model's predictions are fair, no matter what definition of fairness we're using here. Fairness indicators is another tool from Google that we can use to analyze whether our model is fair. And this plugs into TensorBoard, and it's another way of visualizing our TFX pipeline. One really useful feature of it is that it lets us view metrics sliced on features at a variety of decision thresholds. And the decision threshold is the probability score where we draw the boundary between classes for our classification model. So we can potentially change the decision threshold to one that gives us more fair predictions for our model. The other method that we want to mention in the model analysis section is model explainability, which seeks to explain why the predictions made by a model turn out that way. Explainability for machine learning is a big topic, with a lot of active research on the subject happening right now. It isn't something we can automate as part of our pipeline because, by definition, the explanations need to be shown to people. We'll just give you a brief overview here of one tool that fits very easily into our TFX pipeline, the What If tool from Google. But first, what's the difference between explainability and interpretability? These terms are often used fairly interchangeably. Well, in interpretable models, a human can follow the whole decision path through a model. A simple decision tree would be a good example here. But for explanations, these are techniques that give us partial insight into why the model made its predictions. There's a number of different reasons why we might seek to explain our model's predictions, ranging from just building trust in that our model is doing the right thing, to auditing models, explaining the predictions to users, and helping us debug while we're building the model. The what-if tool is another visualization tool that plugs into our TFX pipeline and lets us dig deeper into model predictions at the level of the individual data point. It provides counterfactuals, and for any individual training example, this shows its nearest neighbor from a different class. All the features are as similar as possible, but the model's prediction for the counterfactual is the other class. And this helps us see how each feature impacts the model's prediction for the particular training example. In this case, we see that changing the occupation category is one of the reasons why these two similar examples get put into opposite classes. And another particularly useful feature of the what-if tool is partial dependence plots. And these show how each feature impacts the predictions of the model. It shows us the shape of the dependence, whether it's linear, monotonic, or more complex. Partial dependence plots show the change in prediction results, or inference score, that's on the y-axis for different values of the feature. In this example, we can see that the hours per week feature gives a big change in inference score, but the education category doesn't. These plots contain an important assumption that all features are independent of each other. For most datasets, especially ones that are complex enough to need a neural network to model them, this is a poor assumption. These plots should be approached with caution. They can give you an indication of what your model is doing, but they don't give you a complete explanation.
In the following slides, let's take a look at how we can use machine learning metadata in our machine learning setups and how we can power some of the applications Catherine was just explaining. In real-world scenarios, we often encounter questions around data sets, data schemas. We hear concerns about privacy, and we receive questions around legal compliance of our machine learning models. At the same time, we often have to maintain a variety of machine learning models, so that's why a machine learning inventory would be wonderful, or it would be great to track all the artifacts going in and out of machine learning models during the pipeline process. So this is something we can do with machine learning metadata. And the great thing about TensorFlow Extended is that every individual component runs on the same concept. Every component consists out of 3 parts. It ingests references from a metadata store, provides them to an executor. The executor does something with that, for example, training a machine learning model with a given reference to a training set, and then saves the trained machine learning model somewhere on the file path and stores the reference to that trained model again in the metadata store. And that provides us a very consistent place to where we store the individual metadata. Based on that metadata, we can then build a number of great applications around our business processes and our data science processes in a company or in a project. So for example, we can go back to previous runs and we can investigate why a model potentially didn't perform as we had expected during our training run. We can create model cards to communicate with other stakeholders. We can track the individual artifacts, or we can take care of all the different artifacts going in a machine learning process or machine learning pipeline to produce a new model version. Let's take a look at a few examples. So one of the great examples is an audit trail. So if we use metadata under the hood with our machine learning pipelines, we can then see what artifacts have influenced the model in a particular way. And then we can go back to an exported model and trace all the different steps in our machine learning pipeline which influenced that model all the way back to the raw data. We can see the different changes in the feature engineering. We can see the statistics, the schema, all the different artifacts we generated in our pipeline runs. We can then visualize some of the tools, as Catherine explained, but then we can use them also to collaborate with other team members. Those artifacts and those data, that data is preserved and can be reused and re-visualized later on after the pipeline run has been completed. And maybe we can take this back from an archive and review that with colleagues. We can generate model cards, which are wonderful to communicate the limitations and the constraints of our machine learning models with non-data scientists, for example, product owners or product managers, to highlight what are the constraints or what are our concerns about the machine learning model. And then we can also provide solutions around legal compliances. In the GDPR world, we can often not use the entire data sets, or we have to retrain models with a smaller data set. And in this case, we can use the metadata of our previous training runs and use it in the context of fine-tuning our existing models so that we can, first of all, speeden up maybe updates, but then also fine-tune models with much smaller and newer data sets. And then also we can add the human in the loop. So once our automated pipelines have completed their work, they can ping a data scientist, like in this example here in a Slack channel, and ask for human confirmation or human verification to make sure that everything happened as expected. And once the human signs off, the model will be deployed. If the human rejects the model for whatever reason, the pipeline comes to a stop and the model will not be deployed. And all this together, all the metadata, allows us to provide a high degree of reproducibility of machine learning models, because everything what goes in or out of our machine learning components is being tracked by the metadata store automatically. This isn't experiment tracking. We're talking about artifact tracking of machine learning pipelines, which goes beyond the experiment tracking, what we normally do in our experiments. And then at the same time, we can rerun our pipelines to reproduce the exact same models as we produced them before. And that is wonderful and a great application of machine learning pipelines.
So to wrap up here, in this talk, we've discussed all the steps that you should have in a production machine learning pipeline, starting from your data validation, moving through your model training, looking at model analysis and model validation, to be able to smoothly and automatically deploy your machine learning models. We've seen how metadata underpins this pipeline and provides the foundation for all of the responsible machine learning methods that we can use at each of these steps in the pipeline. Seen how we can check for biased data, add privacy into our training steps, check whether our model's predictions are fair, explain our model's predictions, get a human in the loop to review what our model is doing, and then track what it's been doing via audit trails.
If this was too fast, we highly recommend the publication we just recently published with O'Reilly. You can find all the links on buildingmlpipelines.com. And if you have questions, feel free to reach out via Twitter to us. Thank you.
Thanks very much for tuning in.